Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
A universe governed by smooth, predictable laws found its perfect mathematical language in the calculus of Newton and Leibniz. Their derivatives and integrals describe the motion of planets, the flow of heat, and the arc of a cannonball with sublime precision. These tools operate on functions that are well-behaved, curves that can be examined under a microscope to reveal a straight line. The core assumption is one of local simplicity. Yet, a glance at the world reveals phenomena of a completely different character. Consider the path of a single pollen grain suspended in water, trembling under the unseen, relentless bombardment of molecules. This is the dance of Brownian motion, a trajectory of pure chance. It is a line that is continuous everywhere, yet smooth nowhere. Zoom in on any segment, and you find a chaos as complex as the whole. Such a path has no derivative, no defined velocity at any instant. It is a creature of infinite jaggedness. This presented a profound intellectual impasse. Classical calculus, the most powerful engine of scientific thought for 3 centuries, stalled before the challenge of randomness. The essential tool for accumulation, the integral, was designed for paths of what mathematicians call bounded variation journeys, where the total distance traveled, up and down, remains finite. The Riemann-Stieltjes integral, expressed as the integral of f of t dg of t, could measure the accumulated value of the quantity f along a path g, provided g was sufficiently tame. But the path of a Brownian particle possesses unbounded variation. Its ceaseless, microscopic tremor adds up to an infinite total travel, even over the smallest finite time. The classical integral simply breaks down, its defining sums failing to converge. The mathematics of certainty had no vocabulary for the mathematics of chance and motion. A completely new idea was needed to build a bridge into this chaotic territory. This is the world Kiyosi Itô entered. Working in the 1940s, largely within the intellectual sphere of a Japan recovering from war, Itô absorbed the foundational work that was revolutionizing probability theory. He was a student of the new language measure theory, a framework established by the Russian mathematician Andrei Kolmogorov, which had finally placed probability on a rigorous axiomatic footing, and he was a deep admirer of the French mathematician Paul Lévy, the great intuitive explorer of the strange continent of random processes. Lévy had described the bizarre and beautiful properties of Brownian motion with poetic insight, revealing its fractal-like nature and its profound defiance of classical intuition. Itô's genius was to take Lévy's qualitative descriptions and forge a quantitative, operational calculus for them. He would build the engine that could drive through the landscape Lévy had only been able to map from a distance. Itô's foundational breakthrough was the construction of a new type of integral, one designed from the ground up to handle the violent oscillations of a stochastic process. The Itô stochastic integral, written as the integral of h sub s with respect to b sub s, where h is some process and b represents Brownian motion, looks deceptively similar to its classical cousin. Its heart, however, is entirely different. Like any integral, it is defined as the limit of the sum. We chop a time interval into many small pieces, from time t sub I to t sub I plus 1. On each piece, we approximate the value we are accumulating. The entire character of the integral depends on a single, crucial choice: at what point in time do we evaluate the function h sub s we are integrating. Itô's defining insight was to evaluate h sub s at the beginning of each interval, at time t sub I. This is known as the non-anticipating choice. The value of the sum for a small interval is thus h at time t sub I, multiplied by the change in the Brownian path over the subsequent interval, which is b at time t sub I plus 1, minus b at time t sub I. This choice is a profound philosophical statement embedded in a mathematical definition. It stipulates that the value of our integrand at any moment can only depend on information available up to the moment. It cannot anticipate the random kick the system is about to receive. This aligns the mathematics with the physical reality of causality and the flow of information in time. Any other choice, such as evaluating h in the middle or at the end of the interval, would imply a kind of foreknowledge of the random future, a feature that would make the resulting mathematics useless for modeling real-world phenomena. This non-anticipating construction endows the Itô integral with a property of immense importance. It is a martingale in probability theory. A martingale is the mathematical formalization of a fair game. It is a process whose expected future value, given all information available today, is simply its value today. There is no predictable drift up or down. Because Itô's integral is built by summing up terms where the known part, h at time t sub I, is multiplied by a future random kick with an expected value of 0, the resulting accumulated process is itself a fair game. This martingale property makes the Itô integral the natural and consistent tool for financial modeling, for filtering theory in engineering, and for any domain where one models accumulating effects in an uncertain environment. The radical nature of Itô's construction becomes breathtakingly clear with a single canonical example. In ordinary calculus, the integral of x with respect to x from 0 to some value t is 1/2 t squared. It is a cornerstone of first-year university mathematics. One might naively expect the stochastic equivalent, the Itô integral of a Brownian path with respect to itself, to yield a similar result. When Itô performed this calculation, the result sent a shockwave through the mathematical world. The integral from 0 to t of b sub s with respect to b sub s equals 1/2 b sub t squared minus 1/2 t. There is the ghost in the machine. That additional term, minus 1/2 t, is the signature of the stochastic world. It is a correction, a systematic drift downward that arises purely from the infinitely jagged nature of the path itself. It represents the cumulative effect of the quadratic variation of the process, a measure of its volatility. This term is the mathematical price for integrating along a path of unbounded variation. It is the fundamental departure from the Newtonian world, a clear and unambiguous declaration that the rules of calculus are different here. This single equation contains the seed of the entire theory to follow. Itô's work, while deeply original, stood on the shoulders of giants. The entire edifice would have been impossible without the measure-theoretic probability pioneered by Andrei Kolmogorov in his 1933 monograph. Kolmogorov provided the rigorous language of sample spaces, sigma algebras, and probability measures, transforming probability from a collection of clever tricks into a mature branch of mathematics. He gave Itô the solid ground on which to build. Equally vital was the work of Paul Lévy, who, with his profound intuition, had explored and described the pathological properties of Brownian motion. Lévy was the artist who painted the stunning portrait of this strange mathematical object. Itô was the engineer who built the tools to work with it. The creation of this new calculus had an immediate, though sometimes latent resonance. In a story of tragic coincidence, the German-born French mathematician Wolfgang Dirichlet had independently developed a very similar theory of stochastic integration while serving as a soldier in the French army. Fearing his work would be lost or stolen upon the German invasion, he sealed his manuscripts in a registered letter, *Plaquage sent to the French Academy of Sciences. He took his own life in 1940. His revolutionary papers remained sealed and unread for 60 years, their discovery in 2000 confirming the profound naturalness and inevitability of the ideas Itô had successfully developed and published. In the decades following Itô's publications, it was the French Strasbourg School of Probability, led by Paul-André Mayer, that would become the primary engine for the dissemination and generalization of Itô's ideas in the West. Mayer and his colleagues took Itô's dense and brilliant papers, reformulated the concepts with immense clarity, and integrated them into the broader theory of stochastic processes, offering the definitive texts that would make Itô calculus a central pillar of modern mathematics. They were the evangelists who carried the new language to the world. With his integral, Kiyosi Itô had done something remarkable. He had forged a tool that embraced randomness, allowing mathematicians to finally perform calculus on the very paths that had once broken it. He had provided the first and most essential word in a new vocabulary for describing a fundamentally uncertain world. The profound naturalness and inevitability of the ideas Itô had successfully developed and published found a powerful echo in the decades that followed. It was the French Strasbourg School of Probability, led by Paul-André Mayer, that would become the primary engine for the dissemination and generalization of Itô's ideas in the West. Mayer and his colleagues took Itô's dense and brilliant papers, reformulated the concepts with immense clarity, and integrated them into the broader theory of stochastic processes, offering the definitive texts that would make Itô calculus a central pillar of modern mathematics. They were the evangelists who carried the new language to the world. With his integral, Kiyosi Itô had done something remarkable. He had forged a tool that embraced randomness, allowing mathematicians to finally perform calculus on the very paths that had once broken it. He had provided the first and most essential word in a new vocabulary for describing a fundamentally uncertain world, having established a rigorous method for integration along these erratic paths. A second, equally fundamental question arose. If one could define a quantity like the Itô integral, which itself is a stochastic process, how does this new quantity change over time? More generally, if one takes a standard, well-behaved function, say, the sine of a value, or its square, and applies it to a stochastic process, what are the rules governing the evolution of the result? The classical chain rule from Newtonian calculus, a bedrock of differential analysis, provides the answer for smooth, predictable paths, but for the jagged, fractal-like trajectories of Brownian motion, that elegant rule shatters the very premises upon which it is built. The assumptions of local linearity and vanishingly small second-order effects are violated at every point. A new rule was required, a stochastic chain rule that could account for the peculiar geometry of randomness. The answer Itô provided is perhaps his most celebrated and practically useful contribution, a formula known to generations of scientists and mathematicians as Itô's lemma. Itô's lemma is the computational part of stochastic calculus. It addresses the problem of finding the differential of a function f that depends on time in a stochastic process, x sub t. The classical chain rule would suggest that the change in f is simply the sum of its sensitivities to time and to x multiplied by their respective changes. Itô's insight was to recognize that this was incomplete. His derivation, which can be understood through a careful Taylor series expansion, revealed an additional, startling term. The full statement of Itô's formula for function f of time t and Itô process x sub t is as follows: the differential of f of t and x sub t equals the partial derivative of f with respect to t times dt plus the partial derivative of f with respect to x times dx sub t plus a final term, 1/2 times the second partial derivative of f with respect to x times the square of the differential dx sub t. The first two components of this formula are familiar. The term involving the partial derivative with respect to time captures any explicit time dependence in the function f itself. The term involving the first partial derivative with respect to x is the direct analog of the classical chain rule, representing the change in f due to the infinitesimal movement of the process x sub t. The genius, the entire revolution, is contained in that third and final term. This is the Itô correction, a term that arises directly from the non-zero quadratic variation of the stochastic process. In classical calculus, a term like the square of dx would be of a higher infinitesimal order and would vanish in the limit. For a stochastic process, this is profoundly untrue. The erratic, side-to-side oscillation of a random walk is so violent that its squared displacement, the square of dx sub t, is the same order of magnitude as dt. Specifically, for pure Brownian motion, we have the symbolic yet powerful relationship of the square of db sub t equals dt. This means the second-order term in the Taylor expansion persists, contributing a finite amount to the change in the function. This additional term is a measure of the interaction between the curvature of the function f, given by its second derivative, and the volatility of the process x sub t. It quantifies a subtle but powerful effect, a convex function, one that curves upwards, will experience an upward drift when a random process moves along it, even if the random process itself has zero average motion. The constant random jiggling, when viewed through the lens of a convex function, creates a net positive push. To see the lemma's power and elegance, we can return to the very integral that puzzled mathematicians before Itô. Let us apply Itô's lemma to the simple function f of x equals x squared, with the underlying process being Brownian motion itself, b sub t. Here, the function f has no explicit time dependence, so its partial derivative with respect to t is 0. The first derivative of x squared is 2x, so the partial derivative with respect to x evaluated at b sub t is 2 times b sub t. The second derivative is a constant 2. The underlying process is db sub t, so the squared differential is dt. Assembling these pieces using Itô's formula gives a beautiful result of the differential of b sub t squared equals 2 times b sub t times db sub t plus dt. This single line of calculation is a revelation. It is the differential form of the strange integral result we saw earlier. If we integrate this expression from 0 to t, we find that b sub t squared minus b sub 0 squared equals 2 times the integral from 0 to t of b sub s db sub s plus t. Assuming the Brownian motion starts at 0 and rearranging the terms, we recover precisely the formula for the Itô integral of b sub s of the integral from 0 to t of b sub s db sub s equals 1/2 b sub t squared minus 1/2 t. The lemma provides the missing t, unifying the new forms of integration and differentiation into a single, coherent calculus. It explains, with perfect clarity, where the mysterious 1/2t term comes from. It is the accumulated effect of the process's quadratic variation acting on the convexity of the x-squared function. The development of this formula was a direct and logical continuation of Ito's own intellectual journey. Having defined the integral, he naturally sought the corresponding rules of differentiation that would make the system whole. Ito's lemma was the capstone of his theoretical edifice, the theorem that connected his integral to a new form of differential calculus and, in doing so, made the entire framework computationally tractable. Its influence on others was immediate and transformative. Ito's lemma was a tool that allowed the abstract theory of stochastic integration to be applied to concrete problems. It became the Rosetta Stone for translating problems about the dynamics of random systems into solvable, or at least analyzable, mathematical equations. This impact was felt most dramatically in the world of finance. The economists Fisher Black and Myron Scholes, along with the mathematician Robert Merton, were grappling with the problem of pricing financial derivatives, specifically stock options. They modeled the stock price as a geometric Brownian motion, an Ito process. Their goal was to construct a portfolio of the stock and a risk-free asset whose value would perfectly replicate the option's payoff, thereby eliminating risk and determining a fair price. The crucial step in their derivation, the moment of breakthrough, was a direct application of Ito's lemma to the value of their portfolio. The lemma allowed them to calculate the differential of the option's price, and the magical Ito term was precisely what was needed to construct a riskless hedge. Without Ito's lemma, the Black-Scholes-Merton option pricing model, a cornerstone of modern financial engineering that earned Scholes and Merton a Nobel Memorial Prize in Economic Sciences, would be impossible. Beyond finance, the lemma armed physicists and engineers with a rigorous method for analyzing nonlinear systems subject to noise. It provided a clear recipe for understanding how random fluctuations propagate through complex dynamics, a problem central to fields from signal processing to chemical kinetics. Kiyosi Itô had provided more than a new vocabulary. He had delivered its grammar and syntax. With a robust integral and a powerful chain rule, the stage was now set for the next grand development of the formal construction and analysis of a whole new class of equations designed to model the evolutionary dance of systems driven by the twin forces of deterministic drift and random diffusion. The creation of a coherent integral and a corresponding chain rule provided the essential syntax for a new mathematical language. The question that followed was a profound one. What kinds of stories could this language tell? Classical mechanics, since Newton had its own powerful narrative form, the ordinary differential equation. These equations describe systems whose future is entirely determined by their present state. Given the initial position and velocity of a planet, its entire future trajectory is fixed, unfolding with the certainty of a clockwork mechanism. This deterministic worldview, expressed through equations linking a function to its derivatives, had proven fantastically successful in describing the macroscopic, predictable phenomena of the physical world. Yet, a vast universe of processes operates with a different logic. The jittery dance of a pollen grain on water, the fluctuating price of a security in the marketplace, the noisy transmission of a signal through a communication channel. These systems evolve under the influence of persistent, unpredictable disturbances. Their evolution is a dialogue between a deterministic push and a random shove. To describe such systems, a new class of equations was necessary, one that could weave the thread of randomness directly into the fabric of continuous change. Kiyosi Itô provided the definitive form for these new narrative structures, the stochastic differential equation, or SDE. In its canonical form, an SDE is an object of beautiful economy and immense power. It is written as the change in x sub t equals mu of t in x sub t, all times dt, plus sigma of t in x sub t, all times the change in b sub t. This compact statement describes the infinitesimal evolution of a process, x sub t. It is composed of two distinct parts. The first term, the one multiplied by dt, is the drift. The function mu, the drift coefficient, represents the deterministic tendency of the system, the average direction it would head in the absence of any random influence. It is the analog of the right-hand side of a classical ordinary differential equation. The second term, however, is the revolutionary element, the function sigma, the diffusion or volatility coefficient, modulates the magnitude of random fluctuations. This term is multiplied by dB sub t, the infinitesimal increment of a Brownian motion, representing a purely random shock from a Gaussian distribution. The conceptual leap here is immense. The solution to an SDE is a stochastic process. It is a whole ensemble of possible future paths, each one a unique realization of the underlying random driver. To solve an SDE means to characterize this entire family of trajectories. Ito's formal definition of a solution was a process that satisfied the corresponding stochastic integral equation. This formulation grounded the SDE in the rigorous machinery of his integral, moving it from the realm of physicists' intuition to the world of mathematical certainty. His great achievement was to establish the conditions under which these equations possess well-behaved solutions. He proved seminal existence and uniqueness theorems, which state that if the drift and diffusion coefficients, mu and sigma, satisfy certain technical requirements, specifically a Lipschitz condition and a linear growth condition, then a unique, continuous solution to the SDE exists. The Lipschitz condition, in essence, ensures that the functions are smooth enough to prevent trajectories from diverging wildly from one another, while the linear growth condition prevents the solutions from exploding to infinity in a finite time. These theorems were the bedrock upon which the entire edifice of stochastic analysis would be built, providing the guarantee that the models being constructed were mathematically sound and internally consistent. To see the theory in action, one can turn to a canonical example that predates Itô in spirit but was given its full mathematical life by his framework, the Ornstein-Uhlenbeck process. It is described by the SDE, the change in x sub t equals theta times the quantity mu minus x sub t, all times dt, plus sigma times the change in b sub t. Here, mu represents a long-term mean or equilibrium level, theta is the speed of reversion to that mean, and sigma is the magnitude of the random shocks. The drift term, theta times the quantity mu minus x sub t, as a clear interpretation. Whenever the process x sub t is above its mean mu, the drift is negative, pulling it back down. Whenever it is below the mean, the drift is positive, pushing it back up. This mean reverting behavior makes it an exceptionally useful model for a wide array of phenomena. In physics, it describes the velocity of a particle in a fluid subject to friction and random collisions, a model first proposed by Paul Langevin. In finance, it became a foundational model for interest rates, which tend to fluctuate around a long-term average. In biology, It can model the regulation of gene expression or the membrane potential of a neuron. Ito's framework provided the rigorous validation for all these applications, confirming that this elegant equation indeed generates a well-defined stochastic process. Ito's work, while deeply original, grew from fertile intellectual soil. He was certainly aware of the physical models that had emerged in the early 20th century, most notably the Langevin equation. Physicists had long used such equations heuristically to great effect, but they operated with a degree of mathematical informality, relying on physical intuition to guide their calculations. Ito's contribution was to supply the missing logical foundation. In a poignant episode of scientific history, it was discovered decades later that a young French mathematician named Wolfgang Dublin had, in the late 1930s, independently developed a theory of stochastic integration and differential equations remarkably similar to Ito's. Foreseeing his capture and death as a soldier in World War II, Dublin sealed his groundbreaking work in a package sent to the French Academy of Sciences, where it remained unopened until the year 2000. This parallel development speaks to the intellectual currents of the time and the pressing need for mathematics of randomness. With a formal theory of SDEs established, the final piece of the puzzle was in place. The intellectual toolkit was now complete. Economists like Paul Samuelson had already begun to apply the concept of Brownian motion to model stock prices in the 1960s, extending the even earlier work of Louis Barclier. Samuelson's models captured the essential random walk character of asset prices, but a full dynamic theory for pricing derivative contracts remained elusive. The existing mathematics was inadequate for the task. It was Ito's calculus, with its robust integral, its powerful change of variables formula, and its rigorous framework for SDEs, that provided the precise and necessary machinery. Two financial economists, Fisher Black and Scholes, along with the polymath Robert Merton, would soon take up these tools. They would apply them to the specific SDE describing a stock price and, in a moment of brilliant insight, achieve something extraordinary. They would deploy Ito's mathematics to transform a problem of intractable randomness into one of deterministic certainty, and in doing so, they would forever change the landscape of the global economy. The intellectual framework laid by Paul Samuelson, while pioneering, exposed a fundamental gap in the existing mathematical arsenal. His models, extending Louis Barclay's early 20th century vision, capture the essential random walk character of the asset prices, yet a complete dynamic theory for pricing derivative contracts remained elusive. The mathematics of the era was simply inadequate for the task. It was Kiyosi Itô's calculus, with its robust integral, its powerful change of variables formula, and its rigorous framework for stochastic differential equations, that provided the precise and necessary machinery. Two financial economists, Fisher Black and Scholes, alongside the polymath Robert Merton, would soon take up these tools. They would apply them to the specific stochastic differential equation describing a stock price, and, in a moment of brilliant insight, achieve something extraordinary. They would deploy Ito's mathematics to transform a problem of intractable randomness into one of deterministic certainty, and in doing so, they would forever change the landscape of the global economy. The specific challenge they confronted was the pricing of the European call option. This financial instrument grants its holder the right, with no obligation, to purchase a specific stock at a predetermined price, the strike price, on a specific future date, the expiration date. Before the 1970s, valuing such a contract was a discipline of intuition, experience, and educated guesswork. Traders relied on rules of thumb and a qualitative sense of the market. The value of an option clearly depended on the underlying stock's price, its potential for fluctuation, the time remaining until expiration, and prevailing interest rates. The central difficulty was that the most critical of these variables, the future stock price, was fundamentally uncertain. How could one place a rational, objective price on a promise whose value was contingent on a random outcome? Black, Scholes, and Merton began by adopting a model for the stock price that was a direct descendant of the processes Ito had studied. They posited that the stock price, let us call it S sub t, follows a process known as geometric Brownian motion. This is described by a specific stochastic differential equation d s sub t equals mu s sub t dt plus sigma s sub t dB sub t. Each component of this equation carries a precise financial meaning. The term mu represents the drift rate, the average expected return of the stock over time. The term sigma represents the volatility, a measure of the magnitude of the stock's random price fluctuations. The entire expression is driven by dB sub t, the infinitesimal increment of a Wiener process, the mathematical embodiment of pure, continuous randomness that was at the heart of Ito's research. The equation elegantly captures two essential features of stock prices: their returns are proportional to their current level, and their evolution contains an irreducible element of chance. With this model in hand, they proceeded to their pivotal insight, an idea rooted in the principle of replication. They reasoned that it should be possible to construct a portfolio composed of the underlying stock and a risk-free asset like a government bond that perfectly mimics the financial behavior of the option. If such a replicating portfolio could be created, then, by the fundamental economic law of one price, the value of the option must equal the value of the portfolio created to duplicate it. This was their conceptual master stroke. The execution, however, depended entirely on Ito's calculus. Let the price of the option be C, a function of the stock price S and time T. The goal is to understand how the option's price changes over an infinitesimal time step. Since the option's price depends on the stock price S, and S is a stochastic process, the classical rules of calculus are insufficient. One must invoke Ito's lemma. Applying this powerful formula, the change in the option price, dC, is given by a specific expression, is the partial derivative of C with respect to time, plus mu times S times the partial derivative of C with respect to S, plus 1/2 sigma squared S squared times the second partial derivative of C with respect to S. All of this multiplied by dt. Added to this is the term sigma times S times the partial derivative of C with respect to S, multiplied by dB sub t. This expression appears formidable, yet it contains the key to the entire puzzle. The term multiplying the random component dB sub t is sigma times S times the partial derivative of C with respect to S. The partial derivative of C with respect to S is a famous quantity in finance known as the options delta. It measures the sensitivity of the options price to a small change in the stock's price. Now, consider the replicating portfolio. Black-Scholes and Merton constructed a specific one, a portfolio that is short one call option and simultaneously long a certain number of shares of the underlying stock. The precise number of shares they chose to hold was delta, the very same partial derivative of C with respect to S. The value of this portfolio, let us call it pi, is therefore the value of the delta shares of stock minus the value of the option. The next step is the mathematical climax of their work. They calculated the change in the value of this portfolio, d pi, over an infinitesimal time step. This change is composed of the change in the value of their stock holdings minus the change in the value of the option they are short. When they substituted the SDT for the stock price and the Ito's Lemma expansion for the option price, a moment of profound mathematical elegance occurred. The random components, the terms multiplied by dB sub t from the stock and the option canceled each other out perfectly. The portfolio, constructed with a precise delta quantity of stock, was rendered immune to the random shocks of the market. Its change in value became, for that instant, completely deterministic. A portfolio with zero risk must, in an efficient market, earn the risk-free rate of interest, which we can call R. Any other return would create an arbitrage opportunity, a riskless profit that would be immediately exploited and eliminated. Therefore, the change in the portfolio's value, d pi, must equal R times pi times dt. By equating the two expressions, for d pi the one derived from the portfolio's contents and the one derived from the no arbitrage principle, they arrived at a partial differential equation. This is the celebrated Black-Scholes equation of the partial derivative of c with respect to time plus R times s times the partial derivative of c with respect to s plus 1/2 sigma squared s squared times the second partial derivative of c with respect to s equals R times c. The appearance of this equation marked a revolution. The intractable stochastic problem of option pricing had been transformed into a deterministic problem in the theory of differential equations. Even more astonishing was what had vanished from the final equation. The variable mu, the expected drift or return of the stock, was nowhere to be found. This meant the fair price of an option is independent of the market's collective hopes or fears about the stock's future direction. Its value depends only on observable quantities: the current stock price, the time to expiration, the strike price, the risk-free interest rate, and the stock's volatility. Ito's mathematics had uncovered a deep, internal logic within financial markets, a logic that allowed risk to be perfectly hedged away. The solution to this PDE is the Black-Scholes formula, an equation that would soon be programmed into every financial calculator and trading terminal on the planet. Its publication in 1973 ignited the modern era of quantitative finance. It provided the theoretical foundation for the explosive growth of the derivatives markets, which had since expanded into a multi-trillion-dollar global industry. For this achievement, Myron Scholes and Robert Merton received the 1997 Nobel Memorial Prize in Economic Sciences. Fisher Black had passed away 2 years prior and was ineligible, though his contribution was lauded. The Nobel Committee explicitly recognized the crucial role of the underlying mathematical framework. A quite abstract theory of stochastic integration, born from Kiyosi Itô's deep contemplation of probability, had become the fundamental language for pricing and managing risk throughout the world's financial system. This monumental application demonstrated the astonishing power of Itô's calculus to model and engineer systems governed by continuous chance. Yet for Itô himself, the intellectual journey was pushing ever deeper into abstraction. The same mind that had inadvertently provided the blueprint for modern finance was already contemplating the far more general problem of describing random motion on curved geometric spaces. This next phase of his work would address questions of pure mathematics, seemingly distant from any practical application, yet it would ultimately forge new connections between probability theory and the very structure of geometry itself. This pursuit of geometric generalization led Itô into the rarefied domain of differentiable manifolds, mathematical objects that describe curved spaces like spheres and tori. The central question was profound in its simplicity. How does one describe Brownian motion, the erratic dance of a particle, when the stage itself is curved? The calculus he had forged was built upon the flat, predictable grid of Euclidean space. To transport it to the world of intrinsic curvature required a fundamental rethinking of the very nature of a stochastic path. The problem is subtle. On a curved surface, the direction of movement is constantly being redefined by the local geometry. A random step forward on a sphere is a different kind of displacement from one on a flat plane. Any calculus aiming to describe this process must be invariant. Its physical meaning must remain consistent regardless of the coordinate system used to map the surface. Itô's solution was to develop the theory of stochastic flows of diffeomorphisms. A diffeomorphism is a smooth, invertible map between manifolds, a way of stretching and bending space without tearing it. A stochastic flow, then, can be visualized as the entire space being stirred and churned by a random field of velocities. A particle floating in this fluid would trace a stochastic path. To formalize this, Itô had to confront a deep technical issue concerning the definition of the stochastic integral itself. His own integral, the Itô integral, is a martingale, a property of immense probabilistic power that means its expected future value, given the present, is its current value. This property makes it ideal for financial modeling, where the concept of a fair gain is central. However, when performing a change of variables, a routine operation in differential geometry, the Itô integral requires an additional correction term, a consequence of its forward-looking, non-anticipating definition. This is the famous Itô's lemma. While powerful, this feature complicates geometric manipulations. Concurrently, the Russian physicist Ruslan Stratonovich had proposed an alternative definition of the stochastic integral. The Stratonovich integral possesses a different, equally beautiful property. It transforms according to the standard chain rule of Leibniz and Newton. This makes it geometrically natural, behaving elegantly under coordinate changes. Itô's pivotal contribution in this domain was to construct a rigorous and explicit bridge between his own calculus and the Stratonovich formulation. He derived the precise correction term that translates one into the other. This allowed mathematicians and physicists to move fluidly between the two worlds, using the Stratonovich integral for its geometric elegance and the Itô integral for its probabilistic power, all within a single, coherent framework. He showed that Brownian motion on a Riemannian manifold could be defined consistently, providing a canonical way to model random diffusion on any curved space. This work laid the foundation for what is now known as stochastic differential geometry, a field that fuses the random world of probability with the structured world of manifolds. The implications of this synthesis were far-reaching, opening doors for the next generation of probabilists to ask even more ambitious questions. The French mathematician Paul Malayavin, directly inspired by Itô's framework, sought to build a calculus of variance variations on the space of all possible random paths, the Wiener space. He wanted to understand how a stochastic system would change if one infinitesimally perturbed the entire history of the driving Brownian motion. This required a theory of differentiation in an infinite dimensional space, building upon Itô's rigorous construction of stochastic differential equations on manifolds. Malyavin developed his eponymous calculus, a powerful toolkit for analyzing the regularity of solutions to these equations and for deriving probabilistic proofs of deep results in analysis, like the Hermander theorem on hypervolticity. Decades later, another Fields medalist, Cedric Delarnay, would draw upon this deep well of ideas. Delarnay's work on optimal transport and the mathematical theory of kinetic gases, particularly the Boltzmann equation, explores how systems of particles evolve toward equilibrium. Describing the intricate collision-filled dance of gas molecules involves grappling with both deterministic drift and random dispersion. The language and tools of stochastic analysis, born from Itô's geometric insights, provide a powerful lens through which to analyze the convergence to equilibrium and the propagation of chaos, connecting microscopic randomness to macroscopic emergent laws. Itô's abstract investigations into the geometry of chance had provided the essential grammar for these later mathematical epics. Kiyosi Itô's intellectual journey reveals a quiet and profound dedication to the pursuit of pure understanding. He was a mathematician animated by deep structural questions, by the aesthetic appeal of a coherent theory. There's a beautiful, almost poetic irony that this gentle, unassuming scholar, who by all accounts was indifferent to personal wealth, would become the architect of the mathematical engine that powers global finance. He once remarked with a characteristic, settled with that he was aware his name was attached to these financial formulas, yet he hoped his own pension fund was being managed by someone who understood them well. His motivation was the internal logic of mathematics, the challenge of building a rigorous language for phenomena that had, for centuries, eluded precise description. His ultimate achievement was the creation of this new language. Before Itô, randomness in continuous time was a concept philosophers debated and physicists approximated. It lacked a formal, workable syntax. The tools of classical calculus, designed by Newton and Leibniz to chart the predictable orbits of planets, were insufficient for the task. They described a world of smooth, deterministic flows. Itô's calculus provided the counterpart, a rigorous, operational grammar, for a world permeated by continuous uncertainty. He gave mathematics the vocabulary and the syntax to describe, to model, and ultimately to engineer systems whose evolution is governed by chance. His legacy is the establishment of a fundamental pillar of modern mathematics, a framework that allows us to harness the unpredictable, where Newtonian physics gave humanity the tools to master the clockwork universe. Kiyosi Itô gave us the first reliable tools to navigate the storm.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.